All right, in a previous video, we talked about the fact that protons and neutrons exhibit different amounts of mass in different nuclear arrangements. Just like all systems trying to tend towards lowest energy so that that energy can be shared with its environment, nuclear systems are also tending towards their situation of least energy, which is associated with the nuclear arrangements that have the least amount of mass. In this video, we're going to talk about 3 types of nuclear reactions that nuclei will undergo in an attempt to get to that lowest state of energy. We will remember from the last video that the lowest state of energy exists somewhere around iron 56. So small atoms want to get bigger, and big atoms want to get smaller. The first process we're going to talk about is fission, where large atoms split apart to become small atoms. The most common example of this is uranium-235. This is the nuclear reaction that's used in a lot of different types of nuclear reactors that we use to produce power, in Canada at least. So what happens is if a uranium-235 atom is bombarded with a neutron and becomes the less stable uranium-236, then it can spontaneously break into 2 smaller pieces. What's special about a fission reaction is the 2 pieces aren't going to be the same size, but they're both going to be sort of sizable chunks of the original. So here we have a few possibilities. Uranium could break into barium and krypton, or xenon and strontium, or cesium and rubidium. And what we can see here is that the total mass of these, or the total number of particles, is conserved in these reactions. But again, the energy that's produced in this reaction is going to come from the fact that the protons and neutrons, say in krypton, are going to exhibit less mass than the protons and neutrons did in the original uranium. So that's a fission reaction. It's not like a nice chemical reaction where we're often going to get one product. We can get a lot of different products here, and they're going to occur in a different statistical variation. So maybe the barium and krypton is the most likely, maybe the xenon and strontium is less likely, but when large numbers of atoms are undergoing this fission reaction, we're going to see all of these products being made. Alternatively then, instead of one big thing splitting apart, we can have 2 small things coming together in a fusion process. A common fusion process in the sun, for example, would be when hydrogen with an isotope of mass 3 and hydrogen with an isotope mass of 2, those are called triton and deuteron respectively, although they're just special names for the isotopes of hydrogen, come together to form helium and a neutron. In a future video where I do energy mass equivalence, we can see how this change in mass leads to large amounts of energy. The reduction of the mass of a proton, a neutron, and helium from it in these isotopes of hydrogen is significant. This process where the 2 atoms come together to make one is the most common reaction in stars like our sun, and so this is the reaction that's responsible for producing the energy that heats the earth and all these sorts of things. Those are the 2 big ones, but there is a third type of reaction which happens, which is subtler, and that's a transmutation reaction. This isn't a massive change to the nuclei of an atom, but instead it's small stepwise changes that occur to allow atoms to take on slightly more stable states. This can happen, for example, when we get some ratios between protons and neutrons that are a little out of whack with the typical ratio that protons and neutrons like to exist in, or they can happen specifically with large atoms as they tend towards becoming slightly smaller atoms without going through a fission process. There are 3 main types of products produced in these transmutation reactions, and they have funny names because back when they were discovered, people didn't know exactly what they were. So for example, an alpha decay produces an alpha particle. An alpha particle we can see has a atomic number of 2 and a mass of 4. So now we know that that's helium. But back when they were observing these things and they didn't know what was being produced, they simply gave it the name of the alpha particle. So we still stick with that a little bit. An alpha particle has a charge of 2 plus. Associated with its nuclear charge, we assume that it's not going to have any electrons. The second example here is beta decay. Now a beta particle is either an electron or an electron's antimatter counterpart, the positron. So here what we have is a massless charged release of a particle. So here we can say this alpha particles, they initially thought have mass and charge. Here we have no significant mass and charge. The charge could be positive or negative. Negative is our normal electron, that's what we expect. Positive is a result of the fact that antiparticles exist that have the same mass characteristics of particles but opposite charge. And so in this case, that's what we're seeing with the positron. And finally, the gamma decay that has no significant mass and no significant charge. Now we know that this gamma decay are just high energy electromagnetic waves, just like light, but much higher energy. And like we learned about in the past with atomic transitions where electrons move from high electron orbitals to closer electron orbitals emitting light radiation, here we're emitting an electromagnetic wave that's simply due to rearrangements in the atomic arrangement or the nuclear arrangement where a nucleus goes from a slightly less stable state that it might be in due to a previous nuclear reaction to a more stable nuclear state, and as a result is emitting this electromagnetic radiation, but isn't really emitting a massed particle like we would expect with alpha and beta decay. So again, big stuff splits apart into little stuff. That's called fission. Little stuff comes together to form big stuff. That's called fusion. Transmutation, small changes occur, more like these are sometimes called staircase reactions, where there's very small changes, and so it's just like a staircase where you change your height slowly over time. These can be further classified into 3 basic kinds. Alpha decay, high mass, high charge particle comes out. Now we know that that alpha particle is called a helium atom. Beta decay, positive or negative electrons are emitted, the positive electrons being associated with the antimatter particle of an electron or a positron. And gamma decay, when high energy radiation is released with no significant mass and no significant charge.